Hello everyone, and welcome to this introductory lecture to multivariable calculus. So the main idea that I want to answer, the main question that I want to answer in this lecture is why should we extend calculus to more than 1D? This is a very good question to ask. You could make the argument that isn't calculus hard enough as it is? Why should we extend it to more than one dimension? And I guess a very straightforward and direct answer to that question is, for one, we live in four-dimensional space-time. Specifically, we call it space-time, where you have three dimensions of space, Cartesian coordinates, this is x, y, and z typically, in one dimension of time. So any physical function that we want to model using calculus is going to realistically depend on four things. So what we're going to go through and do in this lecture is I'll just kind of list out a number of different examples and kind of explain their relevance to various majors and why it's actually very important for you to consider multivariable functions. The first example and the first couple examples will all be from various areas of engineering and physics. But if you wanted to describe, say, the temperature, at any point in a room, this is some function of position in time, or in Cartesian coordinates, a function of x, y, z, and t. It's actually a very special type of multivariable function called a scalar field. At every single point in space and in time, we have one specific value defined. That value is the temperature at that point in space and in time. So for instance, kind of draw a picture here to see what we mean. Could have maybe a uniform temperature where at every single point the temperature is constant, which I'll just denote by these gray dots here for every single point in 3D space. But then at some point, if you say turn on a heater at some location and then maybe open up a window at some location, you're going to have that the heat starts to flow out of the room and heat starts to be generated at the point that the heater is at. Let's say the heater is right here, the heat source, and maybe you open up a window right here, and gradually the temperature is going to flow until it reaches some sort of equilibrium. But the idea here is that all of the points' temperatures are going to gradually change from hot to cold, and this change can actually be modeled with a mathematical equation known as the heat equation. Super important in, say, any heat transfer problem that you're trying to solve. This is an example of a multivariable function of 3 position coordinates and a time coordinate. So this is a great first example of a multivariable function. Applications of this abound, but probably going to be most useful in the realm of mechanical engineering, aerospace engineering, civil engineering, in various physical problems you might study as well, so in physics. So this is an example of what's called a scalar field. Another extremely important example is that of an electromagnetic field. And an electromagnetic field is actually not a scalar field. It's what's known as a vector field. At any point in space and time, we typically denote the electric field or the electric field vector as a vector that depends on position and on time. And if we use what are called Cartesian coordinates, which is one of the main coordinate systems we'll be using in the course, this can be described as the x component of the electromagnetic field at the point x, y, z, and t, the y component of the electromagnetic field at this point, and the z component of the electric field at this point in time. We also have corresponding what's called the magnetic field. Same exact idea, but it's actually a different field, and it's related to the electric field through what are called partial differential equations that govern these two fields. Specifically, these are called Maxwell's equations. Again, a little bit later on in the course, we might describe some of these partial differential equations, but the idea here is just to kind of get an idea of how multivariable functions appear in various areas of engineering, physics, and even other areas of many other areas of modern applied mathematics. This is most useful for electrical engineers, for physicists, and really any time that you're considering and you need to consider the electromagnetic field. But the main point here is that the electric field, the magnetic field are both examples of multivariable functions. For another example, we consider it's called the fluid velocity field. If you have a flowing fluid, maybe say air going over an airfoil, or really any number of other applied things that you might want to study involving fluid flow, the fluid velocity field is an essential tool in what's called fluid mechanics, and this is typically denoted as U of RT. Stands for the velocity vector at point R time t. This is a vector field in Cartesian coordinates. Gives you the x velocity of a parcel of fluid, the y velocity of a parcel of fluid, and the z velocity of a parcel of fluid at any given point in space and in time. This is super useful for aerospace engineers, for mechanical engineers, for physicists and physics majors. But the idea here is that both of these examples, the electromagnetic field and the fluid velocity field, are examples of vector fields, not of scalar fields. Now, it should be clear, though, that even though these are vector fields or vector valued functions of position argument, these vector valued functions are still composed of normal scalar functions. We just have multiple scalar functions for each one of these vector fields that we're considering. And so what I want to do now is show a little bit of a demonstration. This is an animation of the exact solution to what's called the two-dimensional wave equation. You get the two-dimensional wave equation in a variety of different modeling contexts, but this 2D wave equation essentially governs you can think of it as governing the displacement of, say, a two-dimensional elastic membrane. This is what's called the linear wave equation. But you can exactly solve this, and this is an animation that I made in my graduate engineering mathematics class using Python. So this is just kind of a visualization program to show a time-dependent plot of the solution to this wave equation. So imagine that you pluck a string here, or not a string, but a membrane in the middle of the membrane, and you want to kind of watch how the membrane is going to be disturbed over a certain length of time. And so I'll hit play here, and we'll take a look at this. This is for what are called two fixed boundaries and one variable boundary. So one of the boundaries, the rightmost in this picture, is free to move up and down, but the other boundaries are fixed. And here you can see the resulting wave propagation and also the correct boundary movement of this membrane. You can think of this almost like a drum head. On the left is what's called a plot of the graph of the displacement function u. On the right is just a visualization using what's called a density plot, which we'll define more in the next few lectures as we kind of get into this. But this is very neat. This is the exact solution to the wave equation. This linear wave equation appears in both electromagnetic field research and in fluid research as well in various contexts. I also want to point out that you can do similar type things for the heat equation and for heat flow problems as well, with regards to temperature. And the next example that we'll look at is what are called stress-strain relations. The stress-strain relationship for general elastic bodies. You could think of an elastic body as like a three-dimensional beam, say, that you're using in constructing a bridge or constructing a building. Let's just kind of draw a diagram here of this in 3D. Let's say you apply some sort of force on this beam at various points. Could be the weight of the building. It could be structural forces due to, say, an earthquake or other wind blowing on the building. But the idea is that we describe these relationships using what's known as it's a tensor, or in slightly less complicated terminology, a very special matrix function of position in time. So we use typically epsilon as the strain function at some point r in time t, where each one of these represents the stretching of the elastic body at a given point. And likewise, we have another matrix function, sigma, the function of position in time, which is the stress of on the body at a point r and at a point t. And this is, again, going to be sigma 1, 1, sigma 1, 2, sigma 1, 3, 2, 1, 2, 2, 2, 3, this is called the strain at point r time t. And the idea is that if this is a scalar field, the temperature is an example of a scalar field, electromagnetic field and fluid velocity field is an example of vector field. This is an example of a tensor field, it's called. And I will not be getting into defining what tensor is in this class, but if you're interested, I recommend after this class taking the course Vector Tensor Calculus, which is almost a direct extension of a lot of the things we'll be talking about in this class. But even though these sound like they may not be, there may be these esoteric objects, they're actually extremely practical and extremely important, because the strain tensor at a given point gives you the amount of stretching this elastic body is doing, and the stress tensor at a given point gives you the amount of forces relative to each axis that you're dealing with. So both linear forces and rotational forces. And what's actually interesting is that both of these, for a linear elastic material, can be combined into what's known as a generalized Hooke's law, which kind of generalizes the Hooke's law in 1D that you hopefully learned about in basic physics class. So this is all I'll say about this topic, but we'll just say here that it's useful for many, many different applications in mechanical engineering, aerospace engineering, civil engineering, and of course physics. You say want to study the stresses and strains on an airfoil wing, so the wing of a plane or a jet, due to fluid that's going over the airfoil wing. It's kind of a combination of this idea of stress and strain and fluid flow, so fluid mechanics. If you're a civil engineer, you want to make sure that your buildings and the materials that you're using in your buildings are designed in such a way that it's not going to fall down, and people don't get hurt. Same thing with bridges, for instance. So it's super useful and super important to understand these things in mechanical engineering and in civil engineering as well. Another very important thing that we will be going over in this class in detail when we get to double and triple integration. So the definite integral is the idea of center of mass. It's also an important concept in electrical engineering as well, because we can also define what's called the center of charge of a body. We can actually do the center of any density function that we want. We can compute the geometric center, which is called the centroid of an object. And then these ideas also lead to what are called moments, specifically in civil engineering and mechanical engineering. The moment of inertia is super important. And in electrical engineering, what's called the moment of charge is very important. And this is related to this idea of if you take, say, this generic structure, maybe some generic beam, in general, the masses in the beam, if we're considering a mass distribution, in general, for real materials, the masses are not distributed evenly throughout the material. The density, the mass density, is going to be different. It's a different multivariable function at different points. So you have a very big conglomeration of mass here, very big conglomeration of mass here, and a very big conglomeration of mass here. And then throughout the rest of the material, it's slightly less so, and there are certain regions where there's really very little mass density. The problem of determining the center of mass of this three-dimensional object can be solved using the triple integral and the ideas that we'll develop in this course. So we'll actually go through these examples near the end of this course. So this is a super useful idea for any mechanical engineering majors, aerospace engineering majors, civil engineering majors, and I'm going to tack on physics here as well, because really all of these are examples from mathematical physics, which is my field of expertise. And this is probably why I like to start off by going over all these physics examples or physics-based examples. But I don't want to leave any major, any area of application out here. The next example that I'm going to talk about is from financial mathematics. So let's say, for example, you have a stock portfolio with N stocks, and so you invest in N companies. Or stonks. As some people like to say. Let's say we invest in N companies, S1, S2, Sn, and specifically that with each one of these companies we're invested at a different percentage. So maybe suppose we're invested in stock I at some percentage Ci, where Ci is a number between 0 and 1, and the sum of all the C values, or all the percentages, has to add up to 1. Because each one of these CIs is a number between 0 and 1, representing the percentage of investment in each individual stock. And then the total returns in a given quarter, say, we call this R, is going to be the sum of C1 times the return in stock 1 plus C2 times the return in stock 2, all the way up to Cn times the return in stock n, where R1 through Rn, right, is the return on each one of these individual stocks for a given quarter. This is a multivariable function of R1 through Rn, where the weights, they're called, the coefficient Ci, are the amount of investment. So in general, what you want to do to maximize your portfolio, or maximize the number of returns, amount of returns that you're getting, is to choose C1 through Cn correctly, so that you're getting the largest return every quarter. But the main example here is that this is a multivariable function, and one of the many real-world examples that we have of multivariable functions. So the areas of interest here would be, say, general applied mathematics, specific financial mathematics, and other areas that are kind of similar to financial mathematics. But really, anyone with a stock portfolio is trying to maximize their returns. So this is a very good example. And the last example that I'm going to touch on is called, from it's an example in computer science. It's a relatively modern example. Only the past maybe 20 years or so has it gotten really big, but this is big data analysis. Specifically, what's called machine learning. And specific algorithm of what are called neural networks. And I'll post a video explaining these. Might be a little bit advanced for us now, but kind of explaining these on the Canvas site for the course. The idea is that specifically, machine learning and neural networks are essentially using multivariable calculus to write an algorithm that learns and gets better at doing whatever you want the algorithm to do. And the applications of this are numerous, right? But the idea here is that one of the big applications that you can do is, say, facial recognition software, the software that Apple or Samsung use to identify you, right, if you use the face scans. And there are many other almost uncountable examples. But the idea here is that this is applied mainly in the big topic in CS, but also in data science in general, and even as far as in IMGD, or interactive media and game development. Because if you want to develop a game that is smart and learns for any, say, task that you're trying to do in the game, this is a very important thing to consider and to use. So this is going to conclude the lecture today. I just wanted to kind of give a number of different good examples of where we can find multivariable calculus in the real world, that we don't even really have to look that hard for. So this is going to give us some motivation for learning the mathematical theory that we're about to embark on discovering over this course. And I hope that I've convinced you, right, that there is an almost uncountable number of real-world applications of the concepts that we're going to be talking about lying around every corner imaginable. So thank you very much for tuning in. I hope you learned something and that you had a great day.